So welcome everybody. We'll start with a few little reminders about homework and projects and all of that.
Yeah, so you should be pretty close to being done with homework 3, so it's due tomorrow at midnight. Unfortunately, Corey is down for maintenance. Hopefully you'll get a chance to, wrap up this afternoon and tomorrow when it is back up again. So just a reminder that on Tuesday of next week during spring break, you're going to have your project proposals due. This is a 2-page maximum short blurb about what you're planning on doing. Give us a list of the students that you're working with, if you are working with other students, and give us some information about what you'd like to pursue so that we can provide some feedback. So I think that's about it. With that, let's get started with the lecture.
Okay, welcome back everybody. Today we're going to talk about one more of the 7 dwarfs or 7 motifs, spectral methods or fast Fourier transforms in particular. And so that's highlighted in blue there. That certainly arises in high performance computing, but it comes up in machine learning and games and all sorts of other areas as well. So here's the outline. I'm going to go back to the basics and define the FFT from scratch, which is just a very special matrix vector multiply, and give you a few fun pictures of the applications of FFTs. I'm certainly using them today because JPEG images are all compressed using FFTs, so I will have some of those in my plot. I'll remind you what the sequential algorithm is on 2 slides, and that will help us then define what the parallel algorithm is for the one-dimensional FFT. But it turns out in practice, people do FFTs not just on one array, one vector, they do it on 2-dimensional arrays or 3-dimensional arrays. In fact, there's a benchmark very much like the LinPack benchmark where everybody races for a 3-dimensional FFT. And for a while, the world record was held based on a CS267 project a little over 10 years ago. And so I'll give you a little history there and say what the design space is for parallel 3D FFTs. And it turns out that FFTs, like matrix multiply, are so commonly used that there are a lot of auto-tuners that people have built and tuned very carefully for different platforms. And I'll dive into one of them. It's called FFTW, which is short for the fastest Fourier transform in the West. And then there's also another similar project called Spiral, which tries to auto-tune not just FFTs, but a whole bunch of different signal processing DSP algorithms. And there's a lot of references here that you can follow up on. So I hope I never use I during this talk as a subscript. It should always mean the square root of -1. So tell me if I make a mistake there. And all of my vectors are going to be indexed from 0. That'll keep the math much simpler. So what is a one-dimensional Fourier transform? I'll call it a discrete Fourier transform. Before I get to the fast version of it, it's a matrix vector multiplied by a very special matrix capital F, whose entries are a magic number omega to the power j times k, where j and k are the subscripts starting at 0. And omega is e to a magic number 2 pi I over m, and that is called an mth root of unity, because if I take that number to the mth power, I get e to the 2 pi I, which is 1. And so that is the particular matrix vector multiply I want to do. That's the one-dimensional version. Now, what do I mean by a 2-dimensional FFT? So in that case, I want to apply it not just to a vector V, but a matrix capital V. And so it consists of pre and post multiplying this matrix by these 2 matrices. So what does the first F times V do? It applies the Fourier transform to every column of V independently. And then when I post multiply by F, it applies the FFT to every row of V independently. And since matrix multiply is associative, I could do it in either order. So that's the 2-dimensional FFT. And of course, higher dimensional FFTs are analogous. So in particular, I'll talk about the 3D FFT. In that case, you do the FFT on all of the sort of vectors in the x direction, all independently, then all in the y direction, then all in the z direction. So where does this come up? The one-dimensional version is, of course, very common in signal processing. I'll give you a picture on the next slide of the most basic example of that. Then I'll tell you about image processing and image compression, and as I said, this is the basic tool in JPEG. And then, since I've been using Poisson's equation as an example throughout the semester, I'll give you a 2-slide summary of how do you almost hit the lower bound for solving Poisson's equation. We talked about multigrid before. The nice thing about Poisson is it gives you the exact solution. It's not an iterative method. And it's even used for something called the fastest known algorithm for multiplying large integers. So suppose you have two b-bit integers and you want to multiply them. There's an algorithm by Schoenhagen and Strassen that can multiply them in time b times log b times log log b. So it's a little bit slower than just one FFT, but actually if you pick b to be really, really large, say the number of atoms in the universe, which is probably an upper bound in any problem size, then log log b is bounded by 8. So it's really b log b in this universe anyway. So let me give you the simplest one-dimensional example, which is for filtering. So I'm going to take a signal, which is just the sum of two sine curves of two different frequencies, 7 and 5, at 128 points. And there it is, this nice, wiggly, smooth curve. And when I take its FFT, because it only is the sum of two frequencies, the FFT is very, very simple. The FFT is complex. So I have the real part plotted here, and I have the imaginary part plotted there. The real part's always 0, and the imaginary part really only has two components. It has a spike corresponding to the frequency at 7, that's right there, and there's, for symmetry reasons, there's another spike there, and then there's a spike of half the size, because the amplitude is a half, sticking down at 5. So that's my initial one. I'm going to take that signal and make it noisy. I'm going to add a random number plus or minus 0.75, in that range, to every value in the signal, and I get this very jagged looking signal. I'd like to recover the original signal from it. Let me look at the FFT. I get lots of noise here and noise here. But this is obviously, there's a much easier to see that there's a signal here. So what am I going to do? I'm simply going to pick a threshold, say 0.25, and I'll take the values in the FFT and set any number less than 0.25 to 0. So all of these get zeroed out except for a tiny spike there and there. And most of this gets zeroed out. And when I undo the FFT to get the signal, then I get back pretty much exactly the original signal I started with. So this is a baby example, but this is very widely used. So let me do a two-dimensional example. And this is used for image compression. So if you want to run this experiment yourself, just start up MATLAB and type load clown, and you'll get this image. And so the idea, so here is a 200 by 320 array of pixels of values. It's a matrix. So what I'm going to do is do the FFT to all the rows, all the columns, and I'm going to compress it by throwing away all the entries that are small. I'm only going to keep the largest 2.5% of all the non-zeros, and then I undo the FFT, and this sort of fuzzy clown comes back. But I only need to store a relatively small amount of information to recover that. As I said, the same idea is used in JPEG, but the way at least one version of JPEG worked, the last time I looked, it would break up this image into little 8x8 blocks. In each block, it would do an FFT, and then it would only keep the leading bits of each component of the FFT. So it would just, use low precision to represent the answer. And that's another way to do compression. So so everybody in the world who looks at a JPEG image depends on this. And then there's Poisson's equation, and I'm just reminding you it's super common, comes up everywhere in all of these different areas of computational science and engineering. And I'm going to show you just how to do the 2D version, but it works for 3 dimensions as well. And so it comes down to solving a system of linear equations. And so the 1D version is please solve L1 for 1D, x equals b. And it's a very simple tridiagonal matrix. And it's based on this stencil. I take 2 times each value, subtract its nearest neighbors. And then the 2-dimensional one is very similar, except it says take each value, subtract 1 from each neighbor to your top and bottom, and subtract each neighbor to your left and right. And that's the system of equations. So the question is, how do I solve in a surprisingly fast way this particular system of equations using the FFT? So it fits on one slide, and it depends on 2 nice facts. The first one is that this matrix L1, with 2's down the diagonal and minus 1's, the FFT tells us what its eigenvalue decomposition is. So the columns of the FFT is basically the eigenvectors, and here's a nice simple formula for all the eigenvalues. I'm not going to do the math, but that happens to be the relationship between Poisson and the FFT. So it's not quite the exact FFT, it's just the imaginary parts, but that's good enough. All the fast tricks I know to make the FFT run fast applies to the imaginary part, the real part, whatever. Okay, So, and then the other observation I make is that the 2D Poisson equation is the same thing as the following. So suppose my unknowns, or I arrange it in an array, so my unknowns are not just a vector, it's this whole array. What does this say? It says, please take 2 times this guy, subtract the neighbors above and below, and then add another 2 times this guy and subtract the neighbors from the left and the right. I can write that down this way. When I pre-multiply x times the one-dimensional Poisson, that's doing the FFT, that's doing the derivative of each column, take 2 times each entry, subtract the neighbors up and down, and this does it on the row, subtracts left and right. So this is going to be how I represent the 2D Poisson equation. And so the trick to solve this super fast is just to substitute the fact that I know the eigenvalue decomposition of L1. So let me substitute L1 equals Fourier transform times diagonal times inverse Fourier transform into this equation. And I'm going to solve that one instead. And so the trick is, let me take my right-hand side, which is my input, and do the FFT on that. And I'm going to represent this as, again, Fourier transform times another matrix times Fourier transform, plug that in, and I see that if I cancel all the Fourier transforms, I'm left with a diagonal system of equations. So this says that this matrix is the input. I do the 2D Fourier transform, and D is a diagonal matrix. These are both diagonal matrices of the eigenvectors for which I have values for which I have a closed form formula, and I just need to solve for x prime. And I can do that. That's just a whole bunch of divisions. It's a diagonal system of equations. And then from x prime, I can go back by doing another 2D FFT to get back x. And so the whole cost is one 2D FFT, a bunch of n squared adds and divisions, and then another 2D inverse FFT. And the whole cost is n squared log n. And so this is, the fastest way if you want to get, the explicit correct answer. There's, modulo round off. This gives you the exact answer. And 3D Poisson would be analogous. So that finishes this table that I've shown you many times. We now hear all the different algorithms you could use to solve Poisson, and we've just filled in that row, which says the cost is the number of unknowns times the log of the number of unknowns. So those are all the applications, and so now given those, I'm going to go on to how do we implement the FFT and how do we parallelize it. But are there any questions about any of these applications before I go on? So in that example, I used the fact that I had to multiply both by the Fourier transform and its inverse. And that's this matrix here. It turns out that all the tricks for multiplying by the Fourier transform and its inverse are essentially the same because the inverse is basically just the complex conjugate. So because this matrix has nice mathematical properties, it's called a unitary matrix. And so it's any trick I can use to multiply by f fast, I can obviously use just by taking complex conjugates to multiply by the inverse fast. For the Poisson equation, I really had to just do the imaginary parts, and that's called, if you want to be careful, the sine transform, because the imaginary parts are the sines of all these angles. And all the tricks that I'm going to tell you for the general case apply to the imaginary part, and they apply to the real part. And since the algorithms are all so similar, we'll just talk about the standard classical complex version. Okay, so here is how you derive on 2 slides the fast algorithm for doing this matrix vector multiply, which would normally take n squared operations, but we're going to do it in n log n. So the observation to make is that all I'm doing when I evaluate this matrix vector multiply is I'm evaluating a polynomial. And so let me just write it down. Here is the dot product of the jth row of the Fourier transform matrix times this vector of coefficients, and I plug in the value. F sub jk is this magic omega to the jk power, and if I put in parentheses there, I am indeed just evaluating a polynomial. The coefficients of the polynomial are just the entries of the vector, and the value at which I'm evaluating it is omega to the j. And so each row of the answer, it's the same polynomial evaluated at a different point. So omega to the 0, omega to the 1, omega squared. And there I've written down the polynomial. So the FFT is the same as evaluating a fixed polynomial of degree m minus 1 at m different points. So what I want to do now is divide and conquer. That's how I'm going to get from m squared to m log n. So what I need to do is figure out how to change this problem of size m into two problems of size m over 2. And that's how I'm going to do the divide and conquer. So here's the trick. Here's that polynomial again. I need to change this into two polynomials of half the degree. That's very easy. I'm just going to take the even coefficients and the odd coefficients and put those together into two different polynomials. So here's the even coefficients, v0, v2, v4, and those are going to get multiplied by the even powers of x. And here are the odd coefficients. They all get multiplied by odd powers of x. Let me factor out x to the 1. They share that coefficient. And now, again, I get x squared, x to the 4th, and x to the 6th. So here I have two polynomials. I'll call this v even with the even coefficients, v odd, with the odd coefficients, and I'm evaluating them all at x squared. So I've made progress. This was a polynomial of degree m minus 1. Here, two polynomials of half the degree. But it looks like I need to evaluate them as many points as I started with. They're not yet problems of half the size. I had to evaluate this at m points. I need to be able to evaluate these at m over 2 points. So here's the trick. It turns out that when I take all of these different values of x, omega to the j, and square them, I get half as many different values, because they all come in plus minus pairs. And so when I square them, those plus minus pairs all collapse to one value. And to see that, if I write down omega to the j plus m over 2 and square it, then omega to the m over 2 squared is omega to the m, which is 1, because omega is an m through divinity. So that value squared is the same as that value squared. So that's why they come in plus minus pairs, basically. So that means I've succeeded in doing divide and conquer. I want to do an FFT on m points, and now all I need to do is an FFT, two FFTs on m over 2 points. And so that's how I'm going to do the divide and conquer. So let me write it down. Are there any questions about that math before I write down the algorithm on? It's just going to be a simple few lines of recursion. So here it is. I'm writing it as a recursive routine. So I'm passing in the vector, the m through divinity and m, just to keep, to make it easy to read. If m equals 1, that's the base case. I don't do anything. I just return the value. It's a constant. Otherwise, I pick out the even coefficients, compute m squared and evaluate this polynomial of degree m over 2 to get this, the values of half the size. Then I take out the odd coefficients, that's v odd, and evaluate that at the same m over 2 points, m's omega squared. Then I get this vector. Now I need to take a linear combination of these two. I need to evaluate this thing with this x there, so I need to multiply by x. And so I need all the powers of omega, but I'm going to use those over and over again, so let me just assume they're in a table. I don't necessarily need to do them here in the inner loop. I've pre-computed them. And then I take x times the odd and add that to v even. And then I notice that because these things come in plus minus pairs, I don't have to do any more multiplies. I'm just going to use the fact that some are plus, some are minus, and I just do a subtract instead. So that's going to save me some of the work. So what's the complexity of this algorithm? Let me call it T of m, T being the time or the number of floating point operations. Well, there are two calls to the problem of half the size, so T times 2 times T of m over 2, and then this is m plus m plus m plus m, so order m more multiplies and adds. Here's a nice simple recurrence, and when you solve it, you get m log m. So that's the classical algorithm. And it's interesting, there's an interesting story about how this came to be known. There was a meeting in Washington of the Defense Science Board in the early 60s. And one of the people at the meeting was Richard Garwin, who was from IBM Yorktown Heights, and he was saying that IBM was spending all this time doing this very, very special matrix vector multiply, and did anyone know of a better way to do it? So one of the other people at the Defense Science Board was John Tukey from Princeton. And he said, I've been teaching this for years, it's trivial. So he wrote it down in the back of an envelope and gave it to Garwin. Garwin went back to IBM, found a programmer to program it up named Cooley, and so they built the algorithm, and then they realized this was going to change the world. And but then they got worried because they knew that Tukey was a consultant for Bell Labs. and they were afraid that Bell Labs might patent it. So Cooley wrote, and Garwin wrote up a paper with Cooley's name on it and sent it back to Tukey and said, would you mind publishing this? And he said, but it was in Gauss's notebooks. He didn't bother publishing it. I don't care. Sure, go ahead. It's trivial. And so that's how it all got published. So, and I was telling this story to Vladimir Rocklin, and who invented the fast multipole method. You'll hear about that later. And he mentioned that when he first learned it, it was in his, he grew up in the Soviet Union, and he learned it from his undergraduate math textbook in 1948. So there's a long history here of how this goes back, but a lot of the paper goes to the, credit officially goes to this paper from the early 1960s. So I met Garwin at a meeting once in Washington, and I decided to thank him for doing this just for fun. But for some reason I decided not to thank him for another important accomplishment. So it turns out that when he was a graduate, a postdoc, he built the first hydrogen bomb. And anybody want to guess who his advisor was? Edward Teller, who founded Lawrence Livermore National Lab. So anyway, there's an interesting history here about all this stuff. So let's now go from that recursive algorithm and try to figure out how to parallelize it. And to do that, I'm going to sort of write down the complete tree of that divide and conquer algorithm, and then ask ourselves, how do we organize it? So let me assume that I'm starting with n equals 16, and with n equals 16, I can represent that by 4 bits. So at the very top, I want to do the FFT, which has a vector with entries with 0, 1, 2, up to 15 as the subscripts, or 4 x's where each x can be 0 or 1. So I'm going to divide that into the even and the odd. That's going to be the first divide and conquer. So how do I look at 4 bits and decide if it's even? That's pretty easy. I just make sure the last bit is 0, right? And I get all the all the even ones. And to make sure it's odd, I'm just going to set the last bit to 1, and that gives me the next set. Okay, that's the first divide and conquer step. I do that again. I look at all of these, and I pick the even ones and the odd ones. So how do I decide if this is even? I take the next bit and I set it to 0. That gives me the even ones. And the odd ones, I take that next bit and set it to 1. And over here, again, I'll take that bit and set it to 0 to get the evens, take that bit and set it to 1 to get the odd ones. And all of this goes down until I get to the very bottom where I actually have specific numbers filled in. And the thing to realize is that if you look at these numbers at the bottom, they're not in normal numerical order. So this one is all zeros. This one is 1 followed by all zeros. This one is 0, 1, 0, 0. This one is 1, 1, 0, 0. They're actually in bit reverse order. So they're coming, so the values, if you run the FFT in this standard way, what this means is the answers are going to come out in a permuted order. Let me just, actually show you what that order is. So here's, 16 numbers sorted in the normal, order. Here's what the output of the algorithm will be. They come out in this funny reversed order, okay? Now, is that a problem? Well, if you wanted to use this output, to do something with it, then you'd have to ask yourself, do I need to permute it? Now, if all you're going to do is, threshold them, set small values to 0, you don't care about the order. And if you're about to do an inverse FFT to get back to the original value, it's just going to bit reverse them again, and they'll come out in the right order. So that's the typical situation. You don't care that it comes out in this permuted order in the middle, because you're going to do an inverse FFT and it'll resort them for you. But depending on your need, you may have to worry about that permutation. So now what I'm going to do, let me just go back to this picture, is ask ourselves, how do I organize this computation in parallel? So what I'm going to do is, again, take this complete DAG, complete description of the case for n equals 16, and draw a plot of all the dependencies in it. Which operations do I perform on which operands, and think of different ways of assigning it to processors. So I'm going to have all of these values as input, and then I'll have another bunch of values which are the outputs of that row and that row and that row. And it looks like this. So here I have 16 dots. Those represent all the inputs. Then at the first stage, when I do my first multiplies and adds, I get another 16 numbers. Those come out at sort of the next level up the tree. And then I do another 16 and another 16, and finally the outputs are right here. and that's what comes out at the end. And so what I've drawn here, and they're all numbered from 0 through 15, and what I've drawn here, all these edges say, to compute this number, what does it depend on? It depends on that edge and that edge, okay? And which one does this depend on? It depends on that one and that one. So to compute the 0th entry, I need to know the 0th one and the 8th one. So going down here, I need to know the 0th one and the 8th one in order to compute that particular value. And to compute the 8th one, I also need 0 and 8. So I have these two edges there. So these solid black lines, if you look at them just by themselves, it looks like a butterfly. And so this is called the butterfly FFT because that's sort of the pattern that appears over and over again here. So to compute 1, I need 1 and 9, and 9 needs 1 and 9, so I have another red butterfly underneath that and so forth. So I get all these little butterflies. That's the first level of recursion. The next level of recursion just flips the next bit. And so now I combine 0 and 4 and 1 and 5 and so forth, but now it's sort of divided into two parts. The next level of recursion flips the next bit, so I combine 0 and 2, 2 and 0, 1 and 3, 3 and 1, and finally at the very top, I'm combining the odds and the evens. So I combine 0 and 1, 2 and 3, 4 and 5. That's the real, combining of odd and even. But this is what it looks like. So each one of these dots represents a multiply and an add, a complex multiply and an add, and all these edges represent the flow of the data. And so the question is, how do I assign this to processors in a way that's load balanced and that minimizes communication? So I want to make sure there is few edges crossing from one processor to another. So there are two ways that there are two natural ways that we talked about for laying out matrices and assigning work. One of them was blocked, and the other one was cyclic. So and I'm going to show that. But so blocked means simply, suppose I have 4 processors, and I have 16 rows here. The first 4 are responsible to the first processor, the next 4 rows go to the second processor, and so forth. That's obvious. The other way, the cyclic way, is just to deal these out like a deck of cards to all the processors. So processor 0 would get that one, that one, that one, and that one. Processor 1 would get that one, and so forth. So let me just try those two and show you what the communication looks like, and then we'll ask ourselves, are these good things to do? So here's the block layout. I have 4 processors, colored green, blue, pink, and brown, and I've assigned, the green processor the first 4 rows and so forth. And so all of these edges are the same as before, but now I've colored them differently, so that if this edge depends on data owned by 2 different processors, I color it black. So this guy depends on some green data, and it depends on some blue data, so I've colored it black. So each black edge represents communication that I have to perform. This one over here has green edges because the green processor owns everything, so all of that is communication free, so to speak. And so if you actually look at this, communication is required for the first log p steps, if I do it this way, and then there's no communication for the last log m over p steps. Okay, so that's the picture I get here. So now let me try the other layout where I assign every 4th row to the first processor and so forth. It looks like this. Okay, so now the picture's kind of reversed. So for the initial steps, I need to combine 0 and 8. Those are both owned by the same processor, the green one, because of the way I've laid things out. So there's no communication necessary there. And the blue guy owns everything there. And indeed, for the first log m over p layers, there's no communication, just as there was before. And it's only at the end, for the last log p steps, there I need the communication again. So these two are kind of reversed, right? So there's, one communicates first and the other one communicates second. So we'd like to have the best of both worlds, obviously, but let me, at least for this one, write down the cost to see what the communication cost of this is. So I'm going to use the simple model we've had so far, which is I'm going to count the flops, I'll count the number of messages, and I'll count the number of words moved. And so both of these two algorithms that I just showed you, the one where it was the blocked layout and the cyclic layout, have exactly the same cost. And so the first one is flops, and it's perfectly parallel, right? Everybody has an exactly equal amount of work to do, which is to say m log m times 2, because I'm doing a multiply and an add, and then divided by p, so perfectly load balanced. how many messages do I need to send? Well, there are log p stages where there's communication. So there's going to be log p messages. And then how much data needs to be sent? Well, every processor has to basically send everything it owns to somebody else. And every processor owns m over p words, and so it's m over p times log p that needs to be sent. And so that's the cost. So now what I'd like to do is get the best of both worlds here to sort of be able to run this algorithm at the beginning, where there's no communication in the initial steps, and then this algorithm at the end, where there's no communication in the final steps. And so that's called the FFT with a transpose in the middle. So what I'm going to do is run the initial algorithm where there's no communication, then change the data structure, and that's going to be called a transpose because it's completely analogous to transposing a matrix. And then I'm going to be in the other layout, which is to say blocked. So it's going to start with cyclic, I'll transpose, it'll be blocked, and then there's no communication again. And so this is all embarrassingly parallel, this is all embarrassingly parallel. What I care about is how much does it cost to do the transpose in the middle. Now, just to be careful here, I'm making an assumption, which is that I can do this initially, and then this later. This costs me log m over p steps, and this is log m over p steps. So this better be at least half of the work, right? So I'm assuming that log of m over p is bigger than log p. That's a perfectly reasonable assumption because that basically means that the number of, that I'm assuming that the length of the vector is at least p squared. And most vectors are much, much larger than p squared, so that's okay. But that is an assumption I'm making at this point. Otherwise, I'd have to do more phases, but I only want to do the transpose once. So now, I claim that going from this cyclic layout to this block layout is a transpose. So let me just sort of convince you of that. So here's the initial layout. It's blocked. So the green processor owns the first 4. The blue processor owns the next 4, and so forth. Here is the cyclic layout I want when I'm done. The green processor should own every 4th, starting with 0. The blue processor should own every 4th, starting with 1. And if you look at these two arrays, they are precisely the transpose of one another. 0, 1, 2, 3, 0, 1, 2, 3. 4, 5, 6, 7, 4, 5, 6, 7. So this is why it's called a transpose, to go from one to the other. So the question is, how much does this cost? So I'm putting all the communication into one step. And so this is going to be an overestimate because a lot of the optimizations are going to actually do pipelining later. I'll go into detail, but let me try it first, assuming I can't pipeline anything, no overlap. The flop costs are just the same as before. It's all perfectly parallel. Now, every processor has to send something to every other processor, and so they're going to be p-1 messages. That's the cost, because every processor is going to have to communicate with all p-1 others. And how much is it going to send? It's going to send, basically everything it owns to somebody, and so this is approximately m divided by p, so everything it owns to everybody else. So if communication is perfectly pipelined, if I were able to overlap all these messages, and I'm going to work real hard at that later in the lecture, then I could make that p-1 go away, so it goes all the way down to alpha. So in other words, it would cost one message if I get to pipeline perfectly. I'm going to try to do that. And then this term is also hitting a lower bound because all my data has to move to somebody else. So this is hitting a natural lower bound, and this one could only if I pipelined. Otherwise, it looks worse than it was before. And this one, I should say, is a factor of log p better. So this is this is the improvement I'm going to get. I'm going to improve by a factor of log p. Okay, so that's the parallel complexity of the FFT. And I'm going to claim this hits a lower bound. And I'm going to tell you a theorem. I'm not going to prove it. And the theorem actually started in the sequential case. And so I'm going to tell you what the lower bound theorem is in the sequential case, and then claim I can hit this lower bound by having a sequential algorithm simulate the parallel algorithm I just showed you. Okay, so here's the sequential case. I want to do an FFT of size little m, and I'm on a cache of size capital M, and this is bad notation, but my little m is bigger than capital M, okay? So it doesn't fit in cache. The question is, how much data has to move between main memory and cache in order to implement the FFT? And the theorem, which goes back to the same paper that first proved the lower bound for matrix multiply, says the number of words moved, assuming you don't, or you're not allowed to do any recomputation, do every floating point operation once, is the number of operations, m log m, divided by the log of the cache size. So you can get some benefit from having a bigger cache, but it's not very much, right? It's only a log m, capital M in the denominator. In contrast, remember, matrix multiply was capital M to the 1/2, and there were big speedups. That was part of homework 1. There's some benefit here, but it's not nearly as much. But that's the lower bound. And this is actually attained by that algorithm I just showed you, where you do this transpose in the middle. So the idea is that the sequential algorithm is going to simulate the parallel algorithm for a carefully chosen value of p. So let me pretend that I have little m divided by capital M processors. So each processor corresponds to all the data that you can fit in cache. And so what the idea is what my sequential algorithm is going to do. It's going to do all the work that the green processor would do here. Pull the memory out of into cache, do the work of the green processor, put it back. Then it'll do all the work of the blue processor in cache, put it back, and so forth. And then, again, when it gets here, it'll get all the data that the green processor would have into cache, do all these flops, put it back. And so the total amount of memory traffic is exactly equal to what the parallel algorithm would do. But the sequential algorithm is just pretending it's the parallel algorithm. And yes. And so, so that's how the algorithm works. Now, it turns out that you can do that without having to do this sort of machine-dependent algorithm where I have to know the cache size. There's a recursive way to do it. If you just run the recursive algorithm that I showed you at the beginning, where the FFT of size m calls two FFTs of size half the size, it'll do this for you automatically as a cache-oblivious algorithm. And these very highly auto-tuned packages that you should use when you want to do the FFT are actually going to use this trick of recursion. They're not going to do recursion all the way down to problems of size 1. They have to stop short, but they will still use recursion in order to hit this lower bound. Okay, that's enough of the sequential case. So let me talk about the parallel case. So what is the parallel cost? This was a theorem that came out about 10 years later. And they said that no matter how much memory you have, there's a lower bound on how much data has to move between processors. And it's lower bounded by, again, the number of flops assigned to each processor, which is m log m divided by p. Can't do better than that. And the denominator also has a factor of the log of the local memory size. If each processor owns 1/5 of all the data, that's the local memory, and again, it's a log term. So it's very totally analogous to what the sequential lower bound would have been. And it also tells you that using more memory doesn't help you. So that trick we had for matrix multiply by replicating the data to go faster doesn't help with the FFT. So this is just this is life. So do we attain this lower bound? Under the assumption that I made, which was that little m is bigger than p squared, that means these two log factors are within a factor of 2 of one another, and again, so we do hit the lower bound on the number of words moved, which is the length of the vector divided by the number of processors. So it is attained by that algorithm in this special case. So in all this theory says we're sort of on the right track, but there's still a lot of tuning to do to overlap communication and computation. So that's where we're going to still get significant speedups, because we have all of those p messages, p times alpha, that I have to worry about overlapping with one another. So just to remind you, this algorithm leaves the data in this permuted order, but I said that was okay for most applications. And I do want to mention there are other parallel algorithms people have thought about doing which give you the approximate FFT. They don't give you the exact FFT. And they depend on the fast multipole algorithm, which is going to come in a later lecture. So they sort of use the fact that we're all solving Poisson, and there are these sort of approximations you can make to actually make the FFT go faster too. And this is, let's say a very beautiful theoretical algorithm. It's not practical yet, maybe someday, but I just wanted to let you know it existed. Okay. So now let's go on to the higher dimensional FFTs, which is where most computer time is spent, rather than doing the one-dimensional version, and talk about the opportunities for overlap. But are there any questions before I go on? Okay. Just to remember, what was a two-dimensional FFT? You have your input is a matrix. You do the FFTs in all the rows and then all the columns. So what are the kind of natural ways to parallelize that, given what we just figured out about the one-dimensional case? Well, I could take my P processors, arrange them in a two-dimensional grid, a square root of P by square root of P grid, and then just do the parallel FFTs on all the rows, with square root of P parallelism, and then do it on all the columns with square root of P parallelism. That's the first way to do it. But there's another way. You could imagine I'm going to use a row layout, so each row is assigned to a processor. So the first processor gets the first n over p rows and so forth. In that case, all the rows are on one processor, so no communication, just run your sequential FFT, and then transpose the data. So now it's stored by column. And then all the FFTs are again completely sequential, and you can just run them all in an embarrassingly parallel way. In that case, all the cost is in the transpose. And the third way to do it, and you can perhaps even imagine more, again, I start with a row layout, so every processor owns n over p rows, so I do all the row FFTs sequentially, embarrassingly parallel, and then I do parallel FFTs on the columns. So I have p-way parallelism on each column. So it turns out that option 2 is going to be best. That's going to give us the most opportunity, doing a transpose in the middle for overlapping communication and computation. So that's going to be the benefit. So the speed up, of course, is going to be limited. So if the communication and the computation both cost exactly the same and I overlap them perfectly, there's a factor of 2. So that's going to be, what I can hope to get in some of these cases. And for a three-dimensional FFT, I'll show you pictures, it's sort of the same idea. In that case, I will take my cube, slice it up into two-dimensional slices, and I'll assign those to different processors. And that way I can do all the, let's say, rows and columns are going to be owned by one processor. That's going to be no communication. Then I have to sort of transpose the cube and then do local FFTs again. So I'll show you pictures of how that works. So the question is, how do I decide what my limit is, my speed limit is for all of this? And so let's get a little closer to the hardware now in terms of our performance modeling. And it's going to be limited by something called the bisection bandwidth. And that's going to, in particular, I'm bringing that up because it's going to limit the speed of doing a transpose operation. So, because every processor needs to send one piece of its data to every other processor, right? So it's sort of everybody to everybody communication. And there's this number that you can measure or define for any topology of a computer, which says how slow does that have to be? And that's called the bisection bandwidth. And the way it's defined is, imagine you take all your processors, divide them into any two groups of P over 2 and P over 2, and ask, what's the total number of messages that I can send? What's the bandwidth between this half and this half? How many messages can I send? And then take the lowest bandwidth across all possible ways of dividing it into two groups of equal size. That's sort of the worst case, and that's called the bisection bandwidth. And if you wanted everybody to talk to everybody at the same time, you'd have to have p-squared wires, right? Everybody would have to be connected to everybody else, and nobody's going to build a computer where the number of wires scales with the square of the number of processors. It's just too expensive, and in time and energy and silicon, and it won't work. So instead, what people do is they have all these other networks that you've heard about in other lectures, and fat trees, dragonfly networks, and so forth. And so those are going to be sort of the limiting fact, and I'm going to show you lots of measurements as we go on toward the end of the lecture where we've tried to implement this. So now let me sort of dive down and ask, so far we've had this simple model where we count the number of messages and we count the number of words moved, and that isn't detailed enough to understand how much opportunity do we have for overlapping communication and computation. So let me go down one more level and talk about something called the log GP model. And so here is the model of what actually happens when you send a message. So in this particular picture, time is on the vertical axis, and here is the axis that says what processor 0 is doing, and on this axis it says what processor 1 is doing. So suppose processor 0 wants to send a message to processor 1. What happens? Well, there's going to be some time spent for processor 0 to take the message, package it up, and let's say send it off somewhere to the network interface card. There's some processor whose job is to talk to the network. That's called the overhead of sending, OSend. Then that processor is free, it's the network's problem, and then we have some time when the network is busy, that's L for latency, when the message is actually moving over the network to processor 1. At that point, processor 1 at some point will get busy and will have to copy the data from its network interface card to its local memory, and that's the overhead of receiving. So how much time is available for processor 0 to do useful work here? So it's pretty clear that this time during the overhead of sending, it's busy, it can't do any useful work. But during this time, latency plus receive overhead, that time could be spent doing useful computation by P0. So there's one other sort of level of modeling here, because I usually don't send just one message. I'm sending lots and lots of messages. And so let's suppose that processor 0 is trying to send lots of different packets, it's breaking it up. And so there's one more hardware parameter, which is called the gap, G for gap. So here, what happens? Processor 0 has some overhead, and then it has to wait a little while before it can send the next message into the network interface card. That's the gap. Then it can start sending another message, and then there's a gap. And so the total amount of time available for it to do something else is from that tip of that arrow to the tip of the next one. So it's gap minus the send overhead. And so that's the amount of time available for overlapping. And there's different versions of this model depending on whether you're sending large messages or small messages. But now let me show you the numbers to indicate what it is on a whole bunch of different platforms. And there's lots of detailed notes at the bottom of the slide that says how you would actually write code to measure this. Because this is an abstract model of very complicated hardware, but there are ways to do benchmarks that are described in the notes. So here's some data about how all this works. And so the reason I call this half the round trip latency is the way you measure this is processor 0 sends to processor 1, then processor 1 sends back to processor 0, and it's all, and then processor 0 measures the time, right? The processor 0's clock is the one that counts. So you take the difference, between sending and then getting the message back. And so all of these times are clustered together for a common machine, but running different software, running different message sending software. So this is a Cray T3E, these three metrics. This is an IBM SP. This is a cluster of workstations running on a Quadrix network. This is all old data, but it just sort of gives you a sense of what can go on. And so here's latency. That was the capital L in the previous slide. Here is the send overhead. That was the OSend in the previous slide. And there's the receive overhead, which was the OReceive in the previous slide. So the time available for overlap for sending a message is blue plus yellow. So that's the amount of time where the processor 0 can actually do interesting, useful work. And so you can see that that's a fair chunk of time, most of it. Now there's one interesting exception here. There's a crosshatch. Now why is that? That's because on this processor, the send overhead and the receive overhead are overlapping. That means processor 1 and processor 0 and processor 1 are both busy at the same time. So how could that be? That's because the way MPI was implemented here is that the two processors had to talk to one another. They had to shake hands and say, processor 0 said, I want to send you a message. Do you have enough space? And processor 1 says yes. And then processor 0 says, oh, okay, here's the message. So they're both busy for a while. And that's, so neither of them can do anything useful during that period of time. That's what was going on in that processor. Okay, so this sort of gives us a hint of what's possible in all these different processors. Yes, so this is just sort of summarizing all of that stuff I was saying. All of this ability to do overlap communication computation is assuming there's this extra processor, which I called a network interface card, could be called direct memory access, so that once the processor has sort of sent off its data, it's free to go on and do something else. So I am making some assumptions about the architecture. And fortunately, a lot of architectures want to support this because overlapping communication and computation is a good thing. And GasNet, which underlies UPC, is one of those systems which provides you a generic interface that does all of this overlapping. So when the processor wants to send a message to the other one, it has the remote address in it. There's no need to match it with a receive. There's guaranteed no handshaking, and there's as much overlap as possible between communication and computation, and that's the UPC model. So this is a good language in which to try to implement these overlapping things. So now let's do some experiments and see how much faster we can make 3D FFTs run. And so here's some performance plots to show you the difference in performance if I'm sending messages using MPI versus GasNet, and why we have more opportunities for overlap. So what I'm doing is I'm sending a really, really large message, a whole lot of data from one processor to another, but I'm breaking it up into pieces of different sizes. And this is on a log scale, so I could be sending all this data in chunks of size 10 bytes, 100 bytes, 1,000 bytes, up to 1,000,000, okay? And the vertical axis is the measured bandwidth, the actual accomplished bandwidth, so up is good. And so you can see that if I'm sending really, really large messages, then both of these, both GasNet in the blue and MPI in the red, reach the hardware peak, which is about 800 megabytes per second. MPI has some problems with larger messages, but if I only wanted to send super large messages, they would be doing about the same. They'd be hardware limited. But the advantage for the overlap comes over here, where I'm sending smaller messages. So this, for example, here says I'm getting nearly the peak bandwidth of the machine, but for a much, much smaller message than the large size, whereas MPI is only getting half the bandwidth. So if I send messages of this smaller size, I'll be able to pipeline them, get nearly full bandwidth, and have lots more overlap of communication and computation using GasNet than if I use MPI. And this plot here is just the ratio of GasNet bandwidth to MPI bandwidth, and it's like a factor of 2 faster over here. So here are, again, another way to measure it. That was on one machine. Here's a whole bunch of different machines where, you take the peak bandwidth that you can get for relatively small messages. This is the GasNet bandwidth. This is the MPI bandwidth, and you can see there's some very large, differences. On this particular machine, it's 13,000 versus 1,000. So how did we get a speed up of 13,000 there? This is a little bit of a cheat. This is a shared memory machine, and MPI copies data anyway if it's on a shared memory machine. But GasNet is smart enough to say, oh, I just have to send a pointer. I don't actually have to move any data. I'm just going to tell you where it is in the shared memory, and that's why it's so much faster. Yeah. Okay, so let's now take these ideas and apply them to this 3D FFT benchmark. So this is part of a collection of benchmarks called the NASA parallel benchmarks. NAS is for NASA Advanced Supercomputing Division. And so they have a whole bunch of different benchmarks they've published that are much more general than LINPACK. And so this is the Fourier transform one. And so the bottleneck, as I said, is going to be this sort of transpose in the middle. There are going to be a lot of different ways to do it. We're going to, the other sort of place where most of the time is spent, of course, is the local one-dimensional FFTs along each row or column. And we're going to use FFTW, which is that tuned, open source tuned version. That's going to give us the best performance available. And and the communication is going to be like 30 or 40% of the runtime. So that's what we're going to try to tune down. So the assumptions that are given to the people who compete in this is that you have a 3-dimensional grid. You start with it laid out in a 1-dimensional way, so each processor gets 2D slices. I'll show you a picture. You can have at most n processors for an n-cube grid, and there's another benchmark which has a large 1D FFT, and you can use all the tricks I'm about to tell you to do an enormous 1D FFT, and you can sort of pretend it's a 3D FFT and use the same tricks. But I'm just going to stick with 3D. Okay, so here's the initial layout. I have this, cube or block of data. It doesn't have to be a perfect cube, so it has dimensions nx by ny by nz. And the initial layout, if I had 4 processors, each processor would get 1/4 of the slices, so nz over p. So that's what it's going to look like. So how am I going to do this? So step 1, obviously I can do all of the columns embarrassingly parallel. Each processor is going to do how many? It's going to be ny times nz over p different FFTs of size this dimension. So that's all local. Then it's going to do all FFTs in the rows. So that's all local computation, no communication. And now it has to do the FFTs in that direction. So we have to figure out how to transpose that. Here's sort of the simplest way to do it. What I need to do is transpose this cube somehow. So let me just think about what I need to do. So this is the initial layout that I started with. This is the layout that I want to in the transpose case. And so what I've indicated here by drawing these dotted lines is which sub-slabs, call this a slab, needs to go to which processor. So this top part, that top quarter part, stays where it is. It doesn't have to move at all. This second quarter of the slab has to be sent to the orange processor. This third quarter has to go to the yellow processor, and the bottom quarter has to go to the blue processor. So that's the communication that I need to perform somehow. And the question is, how do I overlap communication with computation? They're basically, so I'm just repeating, each processor takes its portion of the data, and it has to send it break it up into p pieces, and each of those p pieces, or p minus 1, has to be sent to somebody else. So the question is, how am I going to break up the messages? How am I going to, what size of message am I going to pack together to send to somebody else? And the simplest way to do it is, as this picture suggests, wait until you've finished all the FFTs, take this as one enormous message, and send it to the orange processor all in one, with one MPI sent, and the same for yellow. That I would call packed slabs, so all to all. The other way I could imagine doing it is breaking it up into just two-dimensional slabs. So I could just take this face there, that face, and send it to the orange one, and do some more computation. Take the next face, send it to the orange one. So I could imagine doing it that way. That's slabs, or 2 dimensions. And then I could even imagine doing it after each FFT. So as soon as I finish this FFT of that particular row, I could start sending it to the orange guy. So all of those are different granularities in which I can do that. And as I move from sending one enormous message, but the fewest of them, to down to pencils, I'm going to drastically change the number of messages and the size of each message. So let me show you what sort of an animation of what this looks like. And so in this case, I have a 16 by 16 by 16 cube of data, and it's going to be spread out over 4 processors. So the first processor, say the green one, is going to own 16 over 4, or 4 of these 16 by 16 slices. So what I'm going to do is I'm going to perform all the row FFTs on each one. I'm going to perform all the column FFTs, and then transpose. So I'll start by doing all of those FFTs. This is the slabs. Then I will identify who has to move to whom. So all of these rows get sent to the orange, those and those. And then I pack them all together, and I send them in one message. One message contains all the orange pencils, another message contains all the yellow pencils, and another message contains all the blue pencils. So that's the simplest way to do it. It minimizes the number of messages and maximizes their size. And for the particular case in the NAS parallel benchmark, if I have a 512 by 512 by 512 grid and 64 processors, I'm going to send 63 messages, the fewest I can, and they're all going to be of this very large size. So the number, this times that, is going to be a constant. All these different implementations are going to show you are going to send the same total amount of data, but the number of messages is going to vary significantly. So let's now think about, what happens if I do that? I'm only going to get 67% of peak bandwidth. And so what I need to do is somehow change the way this is organized to make it run better. So now let me, instead of doing it this way, organize it so I break it up into smaller pieces. So here I have n over z, nz over p of these different planes. I'll start by doing all the column FFTs, and then I need to do all of these FFTs on the rows. And so what I'm going to do is I'll start with that one, and as soon as I'm done, I'm going to start sending it to processor 0 and begin doing all the FFTs of those rows. And as soon as they're done, I'm going to send those to processor 1, begin doing the yellow rows, and then pipeline it in that fashion. And that's going to work down the first plane, and then I work down through all the other planes that are available. Okay? And so if I ask how many messages do I send of which size for the NAS parallel benchmark, which is again a 512 cube grid on 64 processors, I'm now sending a lot more messages, but they're a lot smaller. So the product of these two numbers is the same as it was in the last slide, but this has gotten a lot larger, and that's gotten smaller by the same factor. And finally, I have this idea of pencils. And so that tells me as soon as I have a row available, I'm going to send it. So again, I start by doing all the columns locally, and then I need to start doing the rows. So I'll do the FFT of the first row, and as soon as it's done, I'm going to send it to processor 0. Then I'll do the FFT not of the second row, but of the first orange row. And as soon as it's done, I'll send it to processor 1. And then I'll move down to the yellow one, do that one, and do that one. And so then I will keep working my way through all of them in this particular order. So you may ask, why didn't I just do this row, then that row, then that row, and overlap that? And the answer is, this has less network interference, contention, because the part of the network that I use to go from this processor to the green one may be different than the part of the network I use to go to the orange one. So if I sent all of these together, I'd be pushing everything into the same part of the network, and it would get congested. But here, I'm using potentially different parts of the network, so I can get more overlap. And so this is the algorithm that's better to use. And again, for this problem of size 512 cube with 64 processors, I'm going to send 4,000 messages, and each one is going to be of length just one row, which is 8 kilobytes. So let's look at the what performance we can expect. So this is just the size of sending messages, right? I'm not comparing the algorithms yet, but I want to use this to say what we can expect. So there's 3 ways to do this. I send as few messages as possible, and they're all enormous, or I send a medium number of medium-sized messages, or I send lots and lots of tiny messages. Those are the 3 algorithms. So let's ask where on these, and this is just the basic performance and bandwidth of GasNet versus MPI, and so let's ask ourselves, which one do we expect to be best? So based on these numbers and this sort of underlying performance of how the machine works. So if I send as few messages as possible and they're all as big as possible, I'm going to be living over here on this plot where this is the bandwidth for very large messages, and MPI and GasNet are the same. I'm going to hit the peak, but there's going to be the least opportunity for overlap. So that corresponds to packed slabs. That's what I expect. So let me move down to slabs. That is this size message, so at this particular column. And again, MPI and GasNet are going to be about the same, but this has more opportunity for overlap. I don't expect to see much difference between the two. So where is the sweet spot? I claim the sweet spot is right there. And that's because GasNet is still getting nearly the maximum peak bandwidth, but since I have so many more messages, I have a lot more opportunity for overlap, right? I have a lot more, receive plus latency time that I can use. And I expect it to do much better than MPI, because MPI doesn't hit the same peak bandwidth at that time. So this tells us what to expect. So now let us look at some data. And in the interest of reproducible science, here's the set of all the machines that all the data comes from. And I can't really call it reproducible because all these machines are long, dismantled. But anyway, it's as close as we can come. So here are a whole bunch of different machines, and these are all showing the speedups for a variety of different algorithms just for UPC compared to the code that you would download from the website, from the NAS parallel benchmark website. So it's a speed 1, and this is how much better you go. And so blue is using UPC and using packed slabs, so the fewest messages of the largest size, and that always gives you a speed up, but not too dramatic. Then this is when you go to slabs. That's the middle size number of messages for middle number. And then here the pencils. That's the maximum number of messages of the smallest possible size, and it always wins. Doesn't necessarily win by much, depending on the platform, but it gets up to a factor of 1.9. And as I said, the best we could hope for was a factor of 2. So pencils always wins when you're using UPC. And what's interesting is that, so this tells you want to use pencils, but if you just measure the communication cost, if you didn't worry about the overall algorithm, it turns out that the communication time for pencils is sometimes bigger. So here is a plot, which for all these different platforms, and it's comparing UPC with slabs and pencils. Those are the first 2 columns. And it also has MPI, and the vertical axis is time, so down is good. And so you can see that UPC is beating MPI, but you can see that pencils takes more time to communicate than do slabs. On the previous slide, I said the opposite. I said that pencils won, lots of tiny messages. Why is that? That's because this plot here is just the communication. It's not the computation time. It doesn't take the overlap into account. So the fact that I get more opportunity for overlap actually makes the overall thing run faster. And so you can't just look at the communication time. You have to look at that sort of overall chart of how long it takes to finish. And you can see that here there's a missing bar. That's because MPI crashed. It couldn't send all these tiny messages, so it has its own problems. So finally, here is the summary. And so the vertical axis is megaflops. So up is good. And I'm comparing the downloaded Fortran plus MPI code, so not optimized at all on all these different platforms. The next version, the orange one, is the best possible MPI code, which was always using slabs, so the middle-sized messages. And the yellow is always the best UPC code speed, which always sends the pencils, which is the most messages of the smallest size. And you can see that that is the one that's always winning. So that's sort of a summary of what the right way to do overlap is and how these things trade off. Now, this sounds like an advertisement for UPC. Maybe it is. But it doesn't always win. So let me just give you one more piece of information. It wins when the problem is large on this platform. This is the previous supercomputer at NERSC. But it turns out maybe the reason for that is that the people at Cray who were optimizing MPI were optimizing it for small messages, not for large messages. And so here are each of these 3 bars together are a different size 3D FFT. So this is the standard size. This is of half the size, a quarter of the size, of the eighth of the size, and these are getting larger. And the vertical axis is gigaflop, so up is good. The green is UPC, so UPC is winning on the large problems, but MPI is winning on the small problems, and that's because the internals of MPI were just more optimized for sending small messages. So depending on your particular application, you may choose one versus the other, or depending on if Cray comes up with a different version and the UPC people come up with a different version, all of this tuning can change over time. So that's all I wanted to say about tuning 3D FFTs, and I now want to move on to where you get the best code for this, which is to say the fastest Fourier transform in the West. And this is very similar in spirit to other auto-tuners that have probably been discussed in other lectures during the semester. So, Atlas for tuning, the BLAS, and, OSCE for tuning sparse matrix vector multiply. This won, a big award for the best numerical software back in 1999. It's still maintained. So the last release was in October of 2017. And so it's all free. So the people have a commitment to making sure it works. It supports Thread, OpenMPI. I think the last update to MPI was a while ago, so I'm not sure how up to date that is, but they're always adding new architectural support. So the last version added special instructions for Skylake and some new processors like that. So they try to do all this SIMDization too. So now let me just show you some slides about FFTW, and the slides are from the people at FFTW, so they're going to look a little different. So it works for real and complex FFTs, and you can have any size and any dimensionality. So it'll tune not just powers of 2, it does all possible values of n, and that's because they've optimized it to sort of search through this big database of different ways of doing it, and they just try them all and give you the best one. So let me show you some data comparing the performance of FFTW and many, many, many other implementations of FFTs. I mean, a lot of people build FFTs just because it's, they're important, and so they're just claiming here we're the best. And so the horizontal axis is the dimension. This is just for powers of 2. The vertical axis is speed in megaflops. And the solid blue line is FFTW. And in particular, and the dotted blue line is also FFTW. So they have 2 versions. The solid blue line, let me get this right, is what's called out-of-place FFT. That means the output vector does not overwrite the input vector. So the output is a separate vector. And the dotted line is in-place FFT. That's where f times x overwrites x, because you don't want to do that. And so you can see there's some difference in performance there. The solid black line is the vendor's, hand-tuned library. And so you can see they're beating the vendor, significantly on a lot of these different processors. So there's one processor, there's another one, there's another one. All of these are powers of 2. And these are non-powers of 2, just to show you that they also take care of that. And so what are the values? 9, 12, 15, 36, 108, and so forth. So no prime numbers. So all of these, you can still do divide and conquer, because as long as you have an integer factor, you can divide it up into smaller problems. So so something of size 80, you can divide it by 2, you can divide it by 5, and so all those divide and conquer tricks work, but it's not into 2 problems of half the size. It might be into 5 problems of 1/5 the size. And the point is that they do all possible sizes, whereas the vendor doesn't worry about that so much. They just do powers of 2, and so you can get significant performance improvements if you have to use, an unusual value of n. Here is one more advertising slide here. So they also do a lot of work on exploring the whole instruction set. So if you have lots of new SIMD instructions on your platform, they will try all those in all different combinations. And again, sometimes the vendor can beat them, but sometimes they do much better. So how does all this work? Let me skip ahead here. So this is how it works. So there's a special data structure called a plan. This is it basically hides the whole algorithm inside of it. And so what you do to get started is you say, please create a plan to do a discrete Fourier transform. I want the plan to be for a specific dimension. The input and the output vectors are going to be the same, so this is an in-place FFT. It's going to be, here is sort of describing the math, it's going to be a single forward FFT. It could be an inverse FFT, it could be a sine transform, all those different versions. And this is some indication of how much work you want to do to measure it. So for example, you could say, I did the same size yesterday, go look it up in a database. In that case, it would happen a lot more quickly. Then it takes a very long time to figure out, it does a big search over all the different values, and it returns this plan for you as this data structure. And then whenever you need it, you can execute it. So the only reason this is useful, of course, is that the first time you do the FFT, it's going to take a long time to create this plan, but assuming you do lots of FFTs, it will pay off. there's an interesting story, I heard from the people at the MathWorks that they put this into MATLAB at one point, and they got all these complaints from users because when they did the first FFT, it was much slower than it was before, and they just weren't paying attention to the fact that it was much faster after that. So there is a different user experience when you do this sort of auto-tuning. Yes, so as I said, it's the key. This is useful because you're often doing the same FFT size over and over again. So it's going to do recursion, as I said, in order to get all those benefits of minimizing communication. And so this is that same divide and conquer tree that I showed you before. And so if we just did all the 2 size FFTs and all the size 4 FFTs, you'd be running through the whole data structure once, then again, and your total communication would be m times log m, and that would, or n times log n. And so that is nowhere near the lower bound, and so that's why the divide and conquer works. And if you just call it recursively, because of the way recursion works, as soon as everything fits in cache, it'll never touch the memory again. And so if all of that, everything in that side, that yellow box fits in cache, it'll have no more memory traffic. And if you do the math, it actually hits the lower bound. But of course, if you did recursion all the way down to 2 by 2 FFTs, you'd be totally dominated by the cost of the recursion and handling the stack. And so instead, what they do is they figure out what is the right size for the bottom. So at some point they'll say, at this point I'm going to unroll it into no more loops. This is going to be no more recursion, and I'm just going to create. This is what I'm going to build when I do the search. How big should that bottom of my recursion tree look like? And that's part of the what they return to you in the plan. Let me just skip ahead here. Yes, this is called a cache oblivious algorithm because it works for any size. So that's all I wanted to say about FFTW. There's one other package called Spiral from Carnegie Mellon, and this is intended to generate not just FFT software, but hardware as well, and for general DSP algorithms. And at one point they had a website where you could say, I want to do this particular size FFT, I have this particular platform, and enter that onto their website, and they would send you back the optimal implementation. So, and now they have hardware tools too, and I suggest you go to their website for more information. So that brings us to the end here. We've now finished talking about all these different motifs. The only one left is the n-body, and that'll happen after spring break. But other than that, we've done a pretty complete job here, and of course there have been lectures on graph algorithms as well. So, are there any questions before you go off to spring break and write your project proposals? I hope you have a fun spring break too. So, okay, see you later.